back to the third week of modern physics, atomic nuclear particle, and some of the related topics. I'm going to start out this morning with a little bit of review on some of the things we talked about the last couple weeks. Review not because it's going to be important for the final exam, but because each of these things really builds on analogies with the others. So when we start with atomic physics and we talk about where the electrons are in the shells in the atom, when nuclear physics was being developed, when theories were being developed there, it was done by analogy with those same kinds of concepts. And then when we get down to particle physics, it gets stranger and a little more weird, literally stranger, because there's something called strangeness that we'll talk about that applies to elementary particles. But those having a basis in remembering what the more simple pictures are, what the basic atom looks like, and how those shells work, and how the energy levels work, will help us understand a little bit more intuitively some of this very non-intuitive stuff. So I'm going to start out today. The basic topic is nucleons, which are protons, neutrons, the things that a nucleus is made up out of. And go get into hopefully a little bit of particle physics, some of the elementary particles, the real basic constituents of which everything else is made. And we'll talk about how those things are made and how I can arrange them and why things are the way they are. Before we get into that, though, I'm going to review a little bit of atomic physics. I'll just touch on it, and we'll see how Einstein's work led to an understanding of how solar panels work and why sunlight causes cancer, but lights inside don't. We'll talk then, so that's a little bit of atomic physics, a little bit of nuclear physics, where we'll pick up kind of right where we were at the end of last session. This time apply it to atomic bombs, or atomic bombs, nuclear bombs, fusion bombs, fission bombs, and power plants, and see how those things are related and why we have certain kinds of bombs and other kinds of power plants and how that all works. So we'll spend a little bit of time on that. And then what I want to talk about a little bit is experimental nuclear physics. Everything that we've talked about so far, everything we talked about last time, is nuclei as they occur in nature, things that are there naturally. And we don't know them necessarily because we grab them out of nature, but it's all the natural states of things, stuff that's in normal matter. Experimental nuclear physics, though, is where we start poking and prodding the things and spinning them around and changing them a little bit and seeing what happens there. And it's how we develop our understanding of how the nuclear forces work and what these processes are. And that's its own whole section. That's really what doing nuclear physics is like. So I'm going to spend a little bit of time on that, talking about what it's like to do nuclear physics, the kinds of machines that we use, how we do these measurements. That applies directly to the work that I did in graduate school. So I've got a couple of pictures there you'll see of some of the detectors and accelerators and how it all works. The real topics of accelerators and detectors gets much richer and more interesting and way more complicated when we get to particle physics. So that's probably 2 weeks from now. We'll talk a lot about detectors because it's a very rich area and fairly entertaining. This is much more limited. There's only a few things that we're measuring. It's a little easier to understand, but we'll give you a basis for understanding what goes further there. And see how nuclear physics is really done. Then we'll get to nucleon physics. That's what's inside of a proton. We talked a little bit about that. The protons they have an inside. There's stuff inside. There's the quarks in there. And that is a very simple picture that everybody carries around in their mind of what's inside the proton. And we'll see why that's not really true and see how it gets much more complicated, much more interesting, and what really gave rise to all the rest of particle physics right around the late 40s, mid 50s, when suddenly things got way more complicated than anybody had ever expected them to be. It was really it was about 6 months in around 1947 when it looked like particle physics was completely solved. We knew everything. And then it all fell apart. That's why. And then this is where particle physics really begins. This is the line between nuclear physics and particle physics. Nuclear physics has this division within itself of the physics of the nucleus and the physics of the things the nucleus is made out of, protons and neutrons. So that's kind of the boundary we'll bounce around today. And then we get into particle physics, which is really what are these basic constituents of everything. Matter, the energy, how all the forces work. And that's really what will occupy us for most of the rest of the sessions that we have, with some relativity put in at the end, just because relativity is fun, and also applies to a lot of experimental techniques for measuring particle physics, and some quantum mechanics. So with the leftovers, we'll start with that. We had talked about the photoelectric effect. This is what Einstein actually got the Nobel Prize for, not for his work in relativity. And the photoelectric effect, if you remember, I have an atom. In my atom, I have my nucleus, which will have my protons and neutrons in there, in some kind of a ball. And then around that, I have the electrons. They're flying around, and these electrons can be in different shells. So I can be in that shell. If I add more energy, I can move the electron from this shell to that shell. And then I can add energy by adding, throwing an electron in here, and giving the energy there, bouncing it off. I can add energy by throwing a photon in here and pushing it from one state to the next. So if I have a photon, if I add a photon in here, let's try this again. I'm bringing a photon from somewhere, where a photon is a particle of light, so I have some light source. That photon comes into my atom. If the amount of energy in that photon happens to be the spacing, I can push the electron from one orbit up into the next orbit. If I have a photon with enough energy, then I can have enough energy that I can take this electron and free it from the atom. That energy is enough to overcome the attraction between the positive nucleus and the negative electron that's holding them together. If I have more energy than that, the electron is free to go and flies off. So the photoelectric effect, this Nobel Prize winning explanation here, is that if I have a photon above a certain threshold energy, my electron goes away and is free. And if it's below that threshold energy, no matter how many of them I have, I don't get the electron coming off. So we have two consequences here, two things this applies to. Remember, an electron is a negative charge. Negative charge moving. Moving charges is what we call electricity. That's all electricity is. We put it in a wire and it becomes an electric current through a wire. If you don't put it in a wire, it's still electricity that can travel. There's some way for the charges to move. So the picture here now is I have light that comes in and I have electricity that comes out. This is the solar panels. They're sitting on your roof potentially. They're sitting on the telephone poles. It's a material that will take in the light from the sun and result in those free electrons being able to move through the wire, and that gives you that solar power converted into electricity. Now, to do that though, you have to have photons that have enough energy in order to do that. If I have lower energy photons, which is the color of light, or not the intensity of the light, then I won't get any electrons coming off. And then this then is the second piece here, why I can get cancer from out in sunlight. This is a tiny step into chemistry. What chemistry is when I have more than one atom in the neighborhood and they interact with each other in some way. So if I have one atom here and I have another atom here, if they stick together for some reason, that's a molecule. And there goes chemistry. One of the ways they stick together, the way they basically stick together, is by either trading or sharing electrons. So in this case, I have electrons that are here. I have these shells. Each shell can have a certain number of electrons in it. Each shell either wants to be full or empty. And so they'll pass electrons back and forth, or they'll just share an electron between them so that they can both be full. So if I have an electron here, and then maybe I've got two protons here, so I can have the two electrons. By sharing these electrons, that holds them together, because if they split apart, then they can't share the electron anymore, and their shells won't be full. This is what a molecule is, and one of the important molecules that you have is your DNA. Your DNA is a set of molecules that are all linked together in a certain way. Now most things, if I have a molecule in me, and it breaks, nobody really cares. It doesn't do anything. I can't use that piece anymore, but it doesn't matter. But with DNA, if it breaks, DNA is the stuff that gets copied over and over again to make more of your new cells. So if you break that, it's significant. I can put an error into that. And if I put an error into that by breaking how it's connected, what the bonds are, then I'll get mistakes in the copies that are made. And those mistakes in the copies that are made, some proportion of the time, will result in a cancerous cell. It'll keep making copies of that mistake, something that's not supposed to be there. Now, molecular biology is another topic that I could teach another time, but not this time. The important thing here is that if I can break that bond, if something breaks that bond on a regular basis in the DNA, then I get the potential for cancer to emerge from that. Not if it happens once or twice, that has to be a certain set of conditions. But if it keeps happening over and over again, that's what will happen. So when I add that to the photoelectric effect, now if I have a photon coming in here, and it happens to knock out that electron, my bond is broken. And these two atoms are no longer a nice molecule. They fly apart, they spread apart, they're able to drift off. My DNA is broken, and I now have a DNA sequence that says something different than it used to because it's a different set of nucleotides that are encoding the protein. So, again, molecular biology another time. But I've broken this, I've broken my DNA. To do that, remember this photon has to have a certain energy. It has to have enough energy to be able to break the bond, to be able to free the electron. And what determines that energy is the color of the photon, the color of light. That's what the energy of a photon is. So if I'm indoors and I have just regular light coming out of here, that's a little low enough energy, it cannot do that. It's non-ionizing radiation. An ion is an atom that has lost an electron, or potentially gained an electron it shouldn't have. So ionizing radiation is where I have a photon that is of enough energy to kick off one of these electrons. So in this case, ultraviolet light is kind of the line where that happens. Until I get up to ultraviolet light, if I start with red or move up through the rainbow, it's not enough energy to get rid of the electron. It doesn't free it. The photoelectric effect does not apply. When I get to ultraviolet light, that's when that can happen. That's when the electron is kicked off and the bond breaks. So that's why sunlight and UV sunlight is what causes cancer. That's why tanning beds will also cause cancer the same way, because they'll have, in order for that to work, you have their ultraviolet lights that come through. They're just bulbs that produce photons of an energy that's high enough to do that. So that's the end of atomic physics, at least for now. I'll talk a little bit now, jumping a bit to where we left off last time, which was with parts of nuclear physics that are related to bombs and power plants. So what we want to understand here is fission and fusion. And the concepts that we need for that are the two forces. There's the strong nuclear force and the electromagnetic force. Remember, the story of this area of nuclear physics is the balance between those forces. So the strong nuclear force applies over a short range. We'll say that's where the strong goes. And the electromagnetic force is over an infinite range. The electromagnetic force is not as strong, but it's over more distance. So what happens is when I get to a very large nucleus, something like uranium, which has 235 neutrons and protons in it, then I'm really at the edge of where the nucleus is able to hold itself together. So I have all these positive charges. The positive charges want to repel. That's this electromagnetic force. And then I have both between the positive charges and between the neutrons, which are neutral, I have the strong force. The neutrons don't feel the electromagnetic force, so there's nothing pushing them apart. There's just the strong force that's holding them together and holding the protons together. The protons feel both forces, the force holding them together and the force pushing them apart. Remember, this force holding them together applies over a range like that, let's say. It's of narrow range. So as the thing gets bigger, when it's small, that strong force encompasses the entire nucleus and the thing stays together. As it gets bigger and bigger, then because that force, the strong force holding it together is only over a short range, the electromagnetic force can win, and the thing will fall apart. When it falls apart, that's nuclear fission. Most things are either way on one side or way on the other, but there's a region where I can be kind of hanging right on the edge. I'm about to fall apart, and maybe I won't, and so I'll have a certain lifetime, which is how long I can hold out before the electromagnetic force wins out and the thing breaks apart. That's what happens sort of naturally. But when it breaks apart, so I've got, uranium-235. Okay, this is something that happens to have 235 protons and neutrons. if I add one more, uranium-236, just that addition of one more neutron means that now it's bigger, and because it's bigger, because I added one more, that electromagnetic force is able to win, and the strong force is no longer able to hold the thing together. And it splits apart. And when it splits apart, it kind of breaks not exactly evenly. It can break up in different ways into different pieces, but what'll fly off is basically half of a nucleus, the other half, maybe krypton or something, the other half, not exactly half, a different size, and then a couple of neutrons will come off. The reason neutrons come off is because remember, you need this balance between protons and neutrons, but it's not one-to-one. As I add protons, I need to add more and more neutrons to balance out the protons. Because the size is getting bigger and the electromagnetic force is starting to win, I need to keep compensating with more neutrons. So I get more of a strong force component there to keep the thing together. So the ratio of protons to neutrons changes as I get bigger. I end up with more neutrons as I get bigger relative to protons. When I'm small, they can be about even. When I'm really small, one proton's all I need. So because that ratio changes, when I break up, the resulting atoms have fewer neutrons. That means I have extra neutrons left over, and those neutrons go flying off. So I crack my nucleus in half, I get two half-sized nuclei, and 2 or 3 neutrons that come off. Now, if there's another one of these guys just sitting here minding its own business, I've got a uranium-235 sitting there, it will break at some point over some amount of time, naturally. But if I have a neutron coming around and I add it to it, that triggers it to break. Because I'm going from U-235 to uranium-236. That addition of neutron makes it crack a bit.
I'm sorry. Just a question. I thought the neutrons were helping control the strong force. That they were a player in the strong force. So even though you're adding one of those, the fact that it's changing the nucleus size wins over the strong force?
Yes. And the reason it wins is because you're right at the hairy edge. You're about to break anyway. And so that tiny little bit, which normally adding a neutron would help stabilize you,
Yes.
but now adding a neutron destabilizes you, just because you're right at that edge. And it's also, it's not exactly clear when and where that happens. For something like uranium, it's pretty well known. There's a lot of reason that we've invested a lot into understanding certain things, uranium, plutonium, certain familiar sounding names. The less familiar sounding element names, the less familiar nuclei, are not that well understood. And that process of how many neutrons it takes before the thing falls apart is really not well defined in any of, it may not be defined in nature, but it's not defined in any of our models. Adding protons, it's clear. I add one more, it falls apart, that's easy. But with neutrons, it gets really fuzzy, literally fuzzy when you chart it as to where it is, how many is too many. And is there a point where it triggers, or does it kind of go slowly? There's different reasons for that happens.
Just briefly explain what is radioactive decay.
All decay is essentially radioactive decay. Radioactive just means something comes off.
Right.
So if something comes off, it's radioactive. In this case, I have neutrons coming off, that's neutron radiation. I can have alpha particles, which is a small collection of neutrons and protons that come off. It's a helium nucleus, flies off, that's alpha. Gamma is if I have a photon that comes off. And beta is if I have an electron or a positron that comes off. But something coming off, that's what we call radiation.
That happens naturally without any.
Happens naturally, yeah. Uranium-235 will sit there for maybe a minute or something and then break. It's statistical, so you don't know how long it's going to take. But when it breaks, what's one piece I left out? You have the two halves that come off. You have a couple of neutrons or something else that comes off. The neutrons are the important point. And then you also have photons that come off. The neutrons that come off, neutrons are relatively heavy. They move slowly in this case. There's not a lot of energy in them. They kind of bumble around a little bit. The photons are where all the energy is. So when you have, let's say, an atomic bomb that's all that light, all that explosion, that's all the energy from that is in the photons. It's not in the neutrons. The neutrons are slow, we call slow neutrons, or cold neutrons. They just kind of hang around a little bit. Because they're just hanging around, that's why they're available to go to another uranium nucleus nearby and change it from a 235 to a 236 and trigger that next one to fracture. So what I end up with is a chain reaction. I have one uranium that, let's say, naturally breaks apart, shoots off 2 or 3 neutrons, and shoots off some gammas. That's where the energy is. These neutrons here hit another uranium nucleus, and it happens again. And I get 2 more neutrons. And this one will hit another uranium nucleus, and I'll get 2 more neutrons. And I end up with a chain reaction, because each time this happens, each one of these also is shooting off these high energy gammas. So it's a little explosion, creates 2 more little explosions, creates more little explosions, and I get this big chain reaction. This chain reaction will continue as long as I have neutrons flying around, which I'm going to keep having, and as long as I have enough uranium to do this. So if I've got a big ball of uranium, and it's all uranium-235, which is the one that's sitting right on the edge of falling apart anyway, then this will just keep happening. If I don't have enough uranium, let's say I have other things that are in here that are not uranium, that absorbs neutrons, then that neutron is no longer available to go hit the next uranium. So if I put something in here, let's say a big thing of carbon, that absorbs some kind of neutron absorber, then all of these neutrons, as they come off, this will fall apart, send off 2, they disappear, they get absorbed by the carbon. They don't keep the reaction going. So a reaction will only happen if I have enough uranium nearby other uranium in order for it to keep going. And if I have carbon or something else in the way that absorbs these neutrons, then the reaction will not continue to happen. So what I need in order to make an atomic bomb, or we would colloquially call it an atomic bomb, this is not atomic, this is all nuclear. The atoms, the electrons are way up there. To make a fission bomb, what I need is a collection of, first of all, enough uranium, and it has to be pure enough. The reason it has to be pure is because if I have impurities in there, if I have something that's not the uranium, then it'll absorb those neutrons, it won't break, and the reaction, I won't get that chain reaction. That impurity can be other forms of uranium. Uranium-235, the one that does this, is not the most common naturally occurring. It's, if I dig up uranium and I get a piece of it out of the ground, most of it will be 238, with a little bit of 235 mixed in. And this won't happen naturally. The 238 will not break apart when it gets a neutron from one of the 235s. It splits. This will only happen with the 235. So the centrifuges, the purity of the uranium, the enrichment of uranium, all that is really talking about sorting out the 235 from the 238 so I can get enough 235 together so that this chain reaction can happen. So that's the challenge in making a fission bomb, your basic entry-level nuclear bomb, right? It's just getting enough uranium together and getting it pure enough so that this chain reaction can happen. If I can do that, I have a bomb. I don't actually need any other technology. The bomb itself is easy. I just make a big pile of this stuff, and it goes all by itself. I just need to get that uranium together and pure enough in one place.
Why is the 238 more stable than 235? It's a bigger nucleus, so wouldn't it tend to be?
The shapes of the nucleus aren't consistent. I don't have a ball that I just keep adding to. What will happen as I add neutrons is the shape will start to deform in different ways. And the details of how that shape deforms are what really drives whether or not it's stable. And that's actually the subject in experimental nuclear physics is looking at how the shape changes as I make changes to the nucleus. So it becomes very complicated when you get there, and it becomes complicated enough that we do not have a consistent theory. There's no way to predict across the entire range of different nuclei what's going to happen. Each theory applies over a narrow range, and then we do experiments in order to kind of push the boundaries there and keep adapting the theories. But there's no global consistent theory that applies to everything.
Josh, is there any other application for this centrifuge in science beyond making an atomic bomb that you can justify having them and saying, I have them because it's important for the science?
Centrifuges, the idea of a centrifuge is useful in a lot of ways.
Mm-hmm.
I'm sure there's something else you could do with these, but a centrifuge you would build to do this is tuned to do this. And you can separate out other isotopes, but then the main reason you want to separate out other isotopes is for being able to do other kinds of nuclear physics, not making bombs necessarily.
Which uranium is used in nuclear power versus nuclear bombs?
It's the same thing. So what happens here, the picture I drew is a little bit, this is not the bomb picture, this is the power picture. Okay, because for the bomb, all I need to do is get pure enough uranium. And the things, the impurities, are not sitting in a tube of carbon that sits there. The impurities are just things that are naturally occurring, either other forms of uranium or other minerals or other elements that happen to be sitting around where the uranium is. And that's what absorbs the neutrons. If I want to make a power plant, I have two problems. One is I need to make it go, and the other is I need to be able to make it stop, because otherwise I have built myself a nice bomb in my power plant. That's not good for publicity. So what I do is I start again with the pure uranium-235, relatively pure. It's not, we're not talking 90% or anything, but it's some percentage. And that would make the chain reaction start. And I need a way to control it. I need a way to slow it down or stop it if I need to. And that's where this carbon tube, this carbon rod comes in. So I have these carbon rods that are actually on posts that can go up and down. And I have my bowl of uranium-235. And the reaction starts. And it gets a little bit hotter, and I put the carbon in. That starts absorbing the neutrons. Not all of them, but enough of them to slow it down. And then I pull the carbon out a little bit, and it can get a little bit hotter again. And I can use those carbon rods spaced throughout my uranium in order to regulate how quickly this reaction goes and how hot it gets. If I pull the carbon out, then I got a fission bomb. If I put the carbon all the way in, it stops. And you design it so that the carbon can stop it. There's enough of it in there. And you design it that if something goes wrong, the carbon falls in and everything stops. So it doesn't run away by itself or have other kinds of problems. So that's the same thing then. The bomb and the fission for power are really the same process. Now, the one thing that often gets forgotten is how this turns into electricity. A nuclear power plant, all it does, it's just a really hot fire that's easy to make. The way that turns into electricity is the same way coal turns into electricity, which is you boil water, and that boiling water pushes a turbine. And that turbine goes to a generator, and that creates the electricity. So I'm not getting electricity out of my nuclear physics. All I'm getting is heat out of this that I then use to boil water. Until we got to basically windmills and solar panels, every method for generating electricity is boiling water, whatever it happens to be. It's really all you're ever doing with any of this stuff is boiling water. So that's the fission picture, and why we have fission bombs are easy to make, and if you can get the uranium separated, which is the hard part. The technology is old and easy, and again, you don't really need any of it if you have enough uranium. Fusion, though, fusion is much harder. The bomb is much harder to make, and we don't have any fusion power plants, and we really like them. The reason we really like them is because when I take my uranium and I break it in half, I get all kinds of radiation coming off, and then I get other radioactive stuff that comes off. When it breaks in half and I form these two new nuclei, those are not stable either. Those are going to break apart again, and they'll break apart again. They won't necessarily feed the reaction with the neutrons, they might. But what the real problem is that the stuff is going to sit there and be radioactive. I have this radioactive waste. So my nuclear power plant or my atomic bomb, my fission bomb, is going to result in a lot of radioactive material that's hanging around afterward. And now I have a problem because I have no good way to get rid of that. There's really nothing you can do with it. You can seal it up and bury it in the ground. That's pretty much the best you can do. So a fusion bomb, though, wouldn't do that, because remember, a fusion bomb is where I have, simplistically, I have two hydrogen nuclei. These are protons, they're positive. So that positive force wants them to stay apart. And I squeeze them together, and they really don't want to squeeze together. They want to stay apart because of that positive repulsion there. But so I'm pushing them. I have to push them, push them, push them, push them, push them. And if I get them close enough, the strong force in here will start to pull them together. And they'll, boom, snap together and give off a tremendous amount of energy, much more energy than you get out of a fission bomb. So, but I have to get to that threshold. I have to get them close enough. And then the strong force does the work for me and gives me out all the energy. What's left is, if I've got, let's say, two hydrogens, I have helium. Because these things are small and simple, they're very stable. It's easy to make them stable. It's hard to get something that's unstable that's small. Because that strong force, it's so small, the strong force just wins all the time, and it's very easy. So I don't end up with radioactive waste if I do this. So that's great. And I get more energy out, which is great. And my ingredients are not uranium, which is this messy thing I got to dig up out of the ground, or plutonium that I have to make in a reactor somehow. My ingredients are hydrogen. It's basically water. is all I need. So I can make the power out of the water, and I get plenty of power out of it,